So in this section, we're going to find the connection between different coordinate system of a vector space V. So let's look at the first example. So suppose that B is the basis for R2, and suppose also that the B coordinate for the vector X is given by 1, 3. And then how did you find the vector X? Well, X was given by the linear combination of the basis vectors, and its weights were given by 1 and 3. So it's 1 times 2, 1, plus 3 times 1, negative 1, and this equals to 5 and negative 2. And how about on the other hand? Well, suppose that X is given by 3, 0. Then we can find the B coordinate of X by solving the given vector equation, which is given by C1, 2, 1, plus C2, 1, negative 1. So if you write that as the matrix equation, then you get 2, 1, 1, negative 1, C1 and C2. And we've called this matrix as the P sub B, right? Then this tells you that the B coordinate of X, which is given by C1 and C2, equals to, well, P sub B inverse times the vector X, which is the same as, so I think the determinant is given by 1 over negative 2 minus 1, and its adjugate matrix is given by negative 1, 2, negative 1, negative 1, and then you multiply this by 3, 0. Then this gives you negative 1 over 3 times, I guess it is negative 3 and negative 3. So you get 1, 1. So the B coordinate for the vector X is given by 1, 1. So we're going to generalize that in two different sets of the bases. So let's say B to be B1 and B2, and C is a set of C1 and C2, such that these two sets are the basis for the vector space V, where B sub 1 is given by this and B sub 2 is given by that. And suppose that the B coordinate for the vector is given by 3, 1. In that case, we're going to find the C coordinate of X. So if you use the regular algebra, we have the B coordinate of X equals to, well, 3 times B1 plus 1 times B2, right? But if you plug in these two into B1 and B2, then that gives you 3 times 4C1 plus C2 plus negative 6C1 plus C2, where this gives you 12C1 plus 3C2 minus 6C1 plus C2, and you will get 6C1 plus 4C2. So this tells you that the C coordinate for X equals to 6 and 4. But this procedure doesn't use any kind of the linear algebra stuff, so it's really hard to generalize in n-dimensional vector spaces. So let's solve this problem using the linear algebra. So we know that X is given by 3B1 plus B2. So if you take the C coordinate of this one, then we get the same thing on the right hand side. But we know that taking the coordinate is a linear transformation, which means we can separate the addition and factor out the scalar multiplication. So that gives you 3B1 C coordinate plus B2 in C coordinate. Or in other words, we can write this as the matrix equation, which is given by B1 in C coordinate and the C coordinate of B2 multiplied by, I guess, 3 and 1. Or this equals to, well, we have the C coordinate of B1 equals to 4 and 1, and the C coordinate of the B2 is negative 6 and 1. So that gives you 4, 1, and negative 6 and 1 multiplied by 3, 1. And this certainly equals to 6 and 4. So from here, we can tell that, well, the C coordinate of X equals to 6 and 4. So in general, suppose that b sub 1 through b sub n and c sub 1 through c sub n to be two different kind of bases of the vector space V, then we call this matrix as the change of coordinate matrix from B to C, where each column consists of the C coordinate vectors of the vectors in the basis B. And if you multiply this matrix into the B coordinate vector of the X, then we get C coordinate representation of the given vector X. So more specifically, suppose that you have a vector space V over here and a point, a vector X inside V. Then if you take a B coordinate, say this function, the coordinate mapping, then you will get a coordinate, the square bracket of X sub B in Rn. But on the other hand, if you take the C coordinate, then you get another vector in Rn such that the vector X gets sent to the C coordinate vector in Rn. So basically, P sub B to C gives you a map from here to there. So if you multiply by P sub B to C, then you get the C coordinate vector for X. And on the other hand, if you multiply by the change of coordinate matrix from C to B, then you will get the B coordinate vector for X. And this is precisely the same as the inverse matrix for the coordinate transformation from B to C. And this is a generalization of P sub B stuff in section 4.4. So let's say V equals to Rn and E to be the set of standard unit vectors E sub 1 through E sub n. And let's say B to be another basis consisting of B sub 1 to B sub n. Then we know that the E coordinate of X equals to just X itself. Then the formula becomes, the E coordinate for X equals to the coordinate transformation matrix from B to E multiplied by the B coordinate for X. But here, we know that this matrix consists of columns, which is given by B sub 1 sub E through B sub n sub E. But this is indeed the same as the matrix defined by B sub 1 through B sub n. And this is because the E coordinate of any vectors is the same as itself. So suppose that B sub 1 is 9, 1, B sub 2 is -5, -1, and C sub 1 and C sub 2 are these vectors. And consider the basis for R2 given by B1 and B2 and C1 and C2. Then we can find the change of coordinate matrix from B to C, or equivalently P sub B to C equals to B sub 1 sub C and B sub 2 sub C, right? So here, to find the change of coordinate matrix, we have to find the C coordinate representation for B sub 1 and B sub 2, or in other words, we have to solve for this as a linear combination of C1 and C2. Or in other words, if you write this as a matrix equation, then this gives you, I guess, 1, -4, 3, -5 times, A1 and A2. So the C coordinate vector for B1 equals to A1 and A2. And if you multiply the inverse matrix of this one, then this equals to, I guess, 1, -4, 3, -5 to the inverse times -9, 1. Or in other words, it's 1 over, the determinant equals to -5 minus -12. And the adjugate is -5, 1, -3, and 4. And you multiply this by -9 and 1. Or in other words, you will get 1 over 7 and this should be 42 and negative 35, or this equals to 6 and negative 5. Similarly, if you let b sub 2 equals to, say, a sub 3, c1, plus a sub 4, c2, or 1, 3, negative 4, negative 5, times a3 and a4, then you can find the c coordinate of b2 by multiplying the inverse matrix of this again. That equals to, I guess, 1/7, negative 5, negative 3, 4, and 1. And you multiply this to the vector b, which is given by negative 5, negative 1. And this equals to 1/7. I guess you get 28 and negative 21. And this equals to 4 and negative 3. So if you form a matrix using these two as the column vector, then we get the change of coordinate matrix from B to C equals to 6, negative 5, and 4, negative 3. Similarly, we can find the change of coordinate matrix from C to B by writing C1 and C2 as a linear combination of B1 and B2. So we have C1 equals to A1 B1 plus A2 B2, where this equals to, I guess, negative 9, 1, negative 5, and negative 1, and multiply by A1 and A2. Then we can find A1 and A2 again by multiplying by the inverse matrix of this for the both sides. So A1, A2 equals to negative 9, negative 5, 1, negative 1 to the negative 1, or the inverse, multiply by 1, negative 4. And this equals to 1 over, where the determinant is given by 9 minus negative 5. And the adjugate is negative 1, negative 9, 5, and negative 1, multiplied by 1, negative 4, where this equals to 114, negative 21, and 35. And this should equal to negative 3/2 and 5/2. And also by the same argument, we can calculate the b coordinate of C2, well, which equals to the inverse matrix of this matrix, which is given by 1/14, I guess negative 1, 5, negative 1, negative 9. And then you multiply this by the vector C, that is given by 3 and negative 5. Then this gives you 1/14, I guess, well, negative 28, 42. So you get negative 2 and 3 as an answer. So from here, we can conclude that the change of coordinate matrix from C to B equals to, well, negative 3/2, 5/2, and negative 2 and 3. So here, you want to check by yourself that P sub from C to B is in fact the inverse matrix of the change of coordinate matrix from B to C.